The contradictions between Big Bang Theory predictions and observations are not at all limited to those that have been widely dubbed a crisis in cosmology. Despite the theory's continued popularity, virtually every prediction of the Big Bang Theory has been increasingly contradicted by better and better data, as demonstrated by numerous research teams. However, the observations are consistent with a non-expanding universe with no Big Bang. The real cosmological crisis is that the Big Bang never occurred. Before we begin, don't forget to like and subscribe to this channel for more intriguing videos like this, and be sure to watch this video to the end. Therefore, anytime we upload a new video, you will be notified so that you won't miss out on interesting videos from us. Let's begin without further ado. Light elements. Lithium and helium. The Big Bang Theory predicts that certain amounts of light elements, such as lithium, helium, and deuterium, must have been produced in the explosion that is thought to have begun the universe. The prediction for lithium is 400 lithium atoms for every trillion hydrogen atoms. However, astronomers have measured lithium abundances in old stars in our galaxy and discovered that the Big Bang predictions were incorrect. They know the stars formed very early in our galaxy's history because they contain very small amounts of iron and other heavy elements produced by previously existing stars. The lithium abundance in most of these stars is only 160 lithium atoms per trillion atoms, far below the Big Bang predictions. Furthermore, as more data became available in recent years, as described by many researchers, including Spordon, Bonifacio, and Caffau, it became clear that the older the stars, the less lithium there was. Lerner's new study, presented at the American Astronomical Society meeting in January 2020, found that for both lithium and helium, observations of abundances in old stars now differ from predictions by more than a dozen standard deviations, and the gap is growing at an alarming rate. The oldest stars contain less than half the helium and one-tenth the lithium predicted by the Big Bang nucleosynthesis theory. The lowest lithium levels observed are less than 1% of what the theory predicted. Indeed, the evidence suggests that no helium or lithium existed before the formation of our galaxy's first stars. Moreover, the study demonstrates that the correct amounts of these light elements were predicted by an alternative explanation, which hypothesizes that these elements were produced by stars during the early stages of galaxies' evolution. This alternative explanation, dubbed the galactic origin of light elements, GOLE, hypothesis by Lerner, is based on theoretical predictions that the first generation of stars to form in a galaxy are intermediate mass stars that are 4 to 12 times the mass of the Sun. These stars convert hydrogen into helium in tens to hundreds of millions of years, much faster than our Sun's 10 billion-year burn rate. During the final stages of these stars' lives, helium is dispersed in powerful stellar winds. Deuterium and lithium are produced when cosmic rays from these early stars collide with other nuclei at high energy. While these data directly contradict Big Bang predictions, they were predicted and simply explained by theories of galactic evolution that assumed no Big Bang, including Lerner's 1989 paper. Lithium is produced by cosmic rays, which are emitted by early stars and collide with carbon and oxygen nuclei, as well as by stars in their giant phase. Lerner demonstrated that the observed abundances of helium from thermonuclear reactions in early intermediate mass stars and deuterium from cosmic rays could be produced by the same stellar processes that produced the observed amounts of heavier elements like carbon and oxygen. The new study includes new calculations based on the GOLE hypothesis that show that early stars not only produce the observed amounts of helium, deuterium, and lithium, but also carbon, boron, and beryllium in the amounts observed in the oldest stars. The GOLE hypothesis was first published in its entirety in my paper in 1989, and it had been discussed by others even earlier, Lerner explains. Those published predictions have been confirmed by decades of subsequent observations, unlike the predictions of the Big Bang hypothesis. The new work that I am presenting at this conference improves the precision of the predictions and is based on the much more extensive knowledge of stellar evolution that we now have. These findings, based on observations of old stars in our galaxy, are bolstered by recent observations of conditions in newly formed galaxies. These galaxies are ultra-luminous, converting hydrogen to helium at a rate hundreds of times faster than our galaxy. Other researchers' work published in the last year shows that their luminosity is driven by stars with masses of 8 solar masses and above, as predicted by the GOLE hypothesis. A fundamental tenet of the Big Bang theory is the hypothesis that the universe is expanding. However, observations of the size and brightness of thousands of galaxies contradict predictions based on the Big Bang expansion hypothesis, shattering this key pillar, as detailed in a paper published in NNRS by LPP Fusion chief scientist Eric Lerner, titled Observations Contradict Galaxy Size and Surface Brightness Predictions Based on the Expanding Universe Hypothesis, which finds that none of the published expanding universe predictions of galaxy size growth fit all of the physical mechanisms proposed for galaxy growth, such as galaxy mergers, contradict observations. The data, however, are closely fit by the contrary hypothesis that the universe is not expanding, and that the redshift of light is caused by some other, as yet unknown, process. This study puts to the test a startling 1930s prediction of the Big Bang theory. Objects at great distances should appear larger, not smaller. This is due to an optical illusion caused by the galaxies being much closer when their light was emitted, according to the hypothesis. This prediction was repeated in the literature throughout the 1980s, but the Hubble Space Telescope did not confirm it in the 1990s. Instead, Hubble's images revealed that the most distant galaxies appear to be the smallest. A group of researchers then proposed another hypothesis. Galaxies grow in size over time. As a result, very distant galaxies from billions of years ago were thought to be much smaller than present-day galaxies. In this way, the smaller intrinsic galaxy sizes predicted by the 1990s galaxy growth theory neatly canceled out the optical illusion prediction made in the 1930s. Lerner's paper used HST observations from 2004 to 2014 to test the quantitative predictions of galaxy growth theories against the observed sizes of thousands of spiral and elliptical galaxies. The paper limited the samples to galaxies with similar UV brightness. Brighter galaxies are bigger. Lerner also pointed out that the process hypothesized for the growth of elliptical galaxies, mergers with other galaxies, occurs at a rate nearly 10 times slower than expected. A worse observational contradiction is obtained by comparing the gravitating mass of distant galaxies, calculated from rotational speed and size, with the mass of the stars in them, calculated from their emitted light. The size predictions based on the expanding universe result in a gravitating mass that is smaller than the mass of the stars, which is impossible. While predictions based on an expanding universe did not fit the data, Lerner discovered that predictions based on a non-expanding universe fit both spiral and elliptical galaxies at all distances to within a few % accuracies. As predicted by the non-expanding hypothesis, galaxies of a given brightness were the same size regardless of distance in a non-expanding universe. In this hypothesis, the simple linear relationship between light redshift and distance is caused by something that happens to light as it travels, not by space expansion, Lerner explains. Right now, no one knows what could be causing this, but the linear relationship and a non-expanding space make predictions that fit the data, whereas predictions from an expanding universe do not. The current study builds on previous work published in 2014 by Lerner at LPP Fusion with colleagues Dr. Renato Falomo, INAF Osservatorio Astronomico di Padova, and Dr. Ricardo Scarpa, Instituto de Astrofísica de Canarias, Spain. Evidence against dark matter. In its current form, the Big Bang Theory predicts that the majority of matter in the universe is dark matter, which is unlike any matter found on Earth. Earth's increasingly sensitive experiments have failed to find any evidence of the dark matter particles predicted by the Big Bang Theory. However, astronomical evidence has also ruled out dark matter. The relatively low velocities of galaxies in the universe provide the most basic evidence. These can be calculated for galaxies with independent, non-redshift-based distance measurements. The redshifts can then be used to calculate the relative velocities of galaxies. The Big Bang's predicted large amounts of dark matter would generate gravitational forces that would whip galaxies around at hundreds of kilometers per second. However, as Berishev, Silos Labini, Montuori, Pietranero, and Tiracorpi have pointed out, the observed average velocities of 50 km/sec rule out the large amounts of dark matter required by the Big Bang. A super smooth distribution of dark matter required to avoid high velocities would also be incompatible with the lumpiness, inhomogeneity, of matter observed at all scales. Furthermore, the Milky Way's satellite galaxies and the nearby Andromeda galaxy are in a disk configuration, as expected if the gravitating mass is ordinary matter. The satellites would have to be in a random sphere if the gravitating mass was dark matter. As Pavel Krupa and other researchers have pointed out, this evidence completely contradicts the dark matter hypothesis. Perhaps most importantly, and Krupa in 2018 demonstrated that the inevitable viscosity effect of dark matter would cause groups of galaxies to merge so quickly that very few would be observed, in contrast to the many such groups that do exist. Again, there are simpler, non-Big Bang explanations for the data. Perret and Green demonstrated over 30 years ago that electromagnetic forces would produce the constant velocity of rotation in spiral galaxies, which has long been used as evidence of dark matter. These velocities are measurements of the velocity of radio-emitting plasma within a galaxy, which is influenced equally by magnetic and gravitational forces. Jalacha, Bratek, and others have demonstrated that gas moves faster than stars in the outer regions of galaxies, including the Milky Way, and that this difference can be explained by the influence of magnetic fields on the gas. Recently, Kunkel and Covey provided strong evidence of the influence of magnetic fields on star motion. They discovered that a large percentage of nearby stars are embedded in filaments that have lasted hundreds of mi, or even GI. While the authors do not reach this conclusion in their paper, it is clear that gravitational forces alone are incapable of producing long-lasting filamentary structures. Magnetic fields with observed strengths, on the other hand, can dominate the dynamics of dense gas filaments, and these filaments, in turn, can gravitationally control the motion of the stars within them. Magnetic fields, not hypothetical dark matter, can provide the extra confining forces observed in galaxies. Each of these sets of problems could be dismissed as mere anomalies in an otherwise well-supported theory, and in fact, they frequently are. However, when taken as a whole, they contradict all of the theory's predictions, leaving no support at all. And that's all for today, guys. I hope you enjoyed the video, and if you did, please like it and subscribe to our channel so you don't miss out on another wonderful video from us. Till next time.